Hello students, welcome to lecture 12. Today we will study a new topic called validations. We studied several techniques of regularization as a cure to the overfitting problem. In particular, controlling the complexity of hypothesis class was the main focus of the previous class. We have seen that by adding a regularizer term to in-sample error results in augmented error minimization problem, where by minimizing the augmented error, we are controlling the complexity of the model indirectly. Today's lecture will focus on model selection problem and different validation techniques. The validation techniques that we will study today will also help to minimize the effect of model overfitting, in addition to regularization techniques we discussed earlier. In other words, if regularization tried to estimate the overfit penalty so that the minimizing just in-sample error, it would minimize in-sample error plus some overfit penalty, which is a quantity known as an augmented error. Validation techniques instead tries to estimate the actual out-of-sample error and tries to minimize it directly. This class is one of the most important ones that will allow you to select model using techniques such as leave one out cross-validation or v-fold cross-validation techniques. So far, we have covered many different models, such as perceptual learning algorithm, pocket perceptual learning algorithm, linear regression, and logistic regression. Let's say that we have binary classification problem and we want to select the best performing model, given that we constructed a set of models that include perceptual learning algorithm, pocket per PLA, linear regression, and logistic regression methods. Recall that training these models also require additional settings, additional hyperparameter settings, such as the number of trials, number of iterations, eta, the learning rate, different learning rates. And if you want to transform our input data using a transformation function phi, okay, such as it could be linear function, quadratic, or polynomials of 10th degree, Legendre polynomial functions. In addition, one must take into account different regularization parameters. For example, omega of w, right? We can consider L2 norm regularizer, L1 norm regularizer, or symmetry regularizer. We need to choose one of three, and each regularizer comes with a lambda parameter, which also needs to be selected properly. All these different settings of hyperparameters can multiply or sum up and result in 729 different settings of models. And in addition, you may want to try other combinations to get a good G or model hypothesis. Again, our task is to find a model with the best performance measure, namely considering the two central questions of machine learning, which we said before. First, it was, can we approximate with a selected model the unknown target function well enough? Second question was, can we or can the selected model result in best in-sample error performance? Or generally, is there a systematic way of selecting one out of all possible models that answers our two central questions well enough? The answer to that question depends on a model selection strategy adopted. For instance, take a look at the following two different models that was obtained on a given training examples. The examples that are non-linearly separable. As you can see, there are 2 points that cannot be separated by a linear function. Now the question is, which one would you prefer given two different models? We see that on the left, the linear model, okay, H1, cannot separate 2 points, the blue point from the red points perfectly with in-sample error 0. So here, the in-sample error is not 0, right? There are 2 points that cannot be separated. At the same time, on the right-hand side, we see that H2 hypothesis perfectly separates all the points, okay, declaring its own, each point is declaring its own decision boundary. These lines separate. In-sample error is 0 with these kind of nonlinear decision boundaries. Right? However, we know that from VC theory, Vapnik-Chervanenki's theory, that a complex model as this one is not always the best choice. Why? Because the complex model is likely to overfit, or is likely, this case is likely a case of overfitting. From what we have learned in the last lecture, okay? Even if E in sample error is 0, but the out of sample error is expected to be high if you use this kind of complex hypothesis. So in general, the model selection problem focuses on finding the best model with good generalization performance and a model that does not overfit. Okay? Usually, we're talking about M models, not only 2. Given, for example, M models with all different parameter or hyperparameter settings and different complexities, okay, and with corresponding algorithms, whether this is a gradient descent or stochastic gradient descent or some other algorithms that selects one of the hypotheses. And the goal of model selection is to select one of model out of M, let's call it as HM star, okay, such that GM, okay, selected model, that is selected by algorithm based on the data, okay, provides low out of sample error, okay, on selected hypothesis or the model GM star. However, as always, out of sample error remains unknown and it's difficult to calculate as a result because we're dealing with unknown probability distribution or target function. Okay, and then selecting the best model with smallest out of sample error is one of the most important and then practical problem of machine learning. Now, just think about how we could select a model if out of sample error is unknown. Right? This is the first central question in machine learning. Can we select a model, okay, that will approximate our unknown target function in terms of out of sample error performance? Okay, what strategy can we have? Shall we select models using these kind of boundaries visually? Or other alternative better options for selecting the best model out of M, given that out of sample error is unknown? One straightforward way to select a model is to use in-sample error performance as a criteria. Okay? In other words, just select the model which provides best in-sample error given M models. Okay? Select the best one as indicated by M star. That means our criteria, just algorithm based on selects a hypothesis based on data and in-sample error. And we can declare M star, okay, as one of the model with the best in-sample error performance. Then in this case, the H2 would be selected, okay, if you use this criteria. If you use in-sample error as a criteria for selecting the models. Okay. But also we should remember that we potentially run into the problem of overfitting if you consider only in performance, since a model with a more complexity will be chosen each time. That minimizes in-sample error. For example, the polynomial of order 1126 would always be preferred over simple polynomial, linear function, okay? And then when it comes to regularization parameter lambda 0 would always be more preferred over lambda 0.1, for example, which would restrict the hypothesis from achieving in sample 0. Well, lambda 0 doesn't affect, will not control the complexity of the hypothesis. Okay, if we consider further two models, A1 that minimize in sample over the set of H1 hypotheses, and A2, the algorithm that minimize in sample over the next set of hypotheses, different set of hypotheses, H2. The best model would be selected as GM star with minimal in-sample error over the union of two hypotheses, right? H1, the union of H2. This way of selecting model and plus the learning would have to pay the price of complexity. Okay, in terms of VC dimension, Babnik-Chervonenkis dimension. As we know that a hypothesis with a higher VC dimension leads to a bad generalization or to overfitting. While in sample, in bad generalization, even if in sample is small, the out of sample would be large. Okay, and that doesn't answer the first question of machine learning well enough. We cannot make sure the model selected using in-sample error criteria would generalize well or approximate well the target function and would result in small out-of-sample error. We can conclude that selecting a model using in-sample criteria is quite dangerous, in a sense that, again, the model will not generalize outside the training dataset, okay, and potentially will overfit. Next, another strategy. What if we consider selecting a model by using Etest performance measure? In this case, we can train a model using the training data and use dtest or test dataset to select the model using the Etest performance measure. It's a test performance measure. And select M star among all models based on data, and it is performance on d-test, assessed by test performance, right? So it can be shown that the generalization using a finite bin Hofting and VC dimension, that if we use Etest, the following bound holds, the out of sample error for the GM star is upper bounded by Etest performance. Okay, this is not in sample error, but E-test error plus a complexity term, considering the union bound of all hypotheses, which provides here the good generalization guarantee. However, where can we get the d-test? We don't know. We don't have access to the d-test. The d-test is a data set that is unknown and is expected to capture the true distribution of the data generated by target function. All right, so selecting a model using e-test would be the best option. However, it is infeasible to calculate e-test. We don't have access to d-test. If we compare two above mentioned approaches, the possible strategy in model selection, namely, one is based on in-sample error, the other is based on e-test error. We know that E-in can be calculated easily from the available data, which is feasible on hand. Right? However, the data is contaminated, as the same data is used during training and selecting the model. This in turn result in possible overfitting and poor generalization problem. Now, if we consider the e-test case, select a model based on e-test performance. Here, e-test would be calculated from independent d-test data, right? However, we don't have d-test data at hand. Therefore, it's not feasible to calculate e-test performance of a models and select one. Okay, to select a model based on this performance would be impossible. Now the question is, can we come up with a feasible criteria? Something in between, in sample error or test error. A different performance measure, which can be calculated from dataset, which is not contaminated during the training. The answer is yes. We can consider a metric called e-validation, which lays between in sample error and test. Okay, so we call it e-validation error that can be calculated by allocating a part of the entire training dataset that we have at hand. So e-validation will be calculated from the validation error measure dataset, right? And it's a part of our entire dataset that has not been used. So this is feasible on hand, and it is clean because we will not use the validation dataset during the training and selecting a model using our algorithm, right? Then selecting, we can hope a model via e-validation would be a better approach than selecting a model using in-sample error or e-test error. Okay? An entire training dataset, size of n. We divide this dataset into dtrain, which is the size of n minus k, and dval, validation dataset, which is the size of k, right? And we calculate the validation error using the dval, the validation dataset, on a hypothesis that has been selected using the dtrain, or training dataset, which is of size n minus k. Okay, so our algorithm select the gm and then this minus using the dtrain, while initially the in-sample error was computed using the entire dataset, and our algorithm selects the gm using, again, the entire dataset. Note here, the g minus m represents the hypothesis that has been selected from the dtrain, the part of the training or part of the dataset called dtrain. And the validation set here is a subset of the entire dataset, which we can call it as on-hand simulation of a test set that we can use to evaluate our model's performance. Now, in order to connect evalidation, to out of sample error, out, here we can consider validation set to estimate the actual out of sample error and minimize it directly. As this validation is not involved during the training. The e-validation is considered as a better proxy of out of sample error. Okay, so validation is clean, that has not been contaminated. And besides, all validation examples still can be assumed to follow independent, okay, identically distributed by a probability distribution, joint probability distribution. Right? And also, we select k examples randomly from the dataset. So there are some randomness involved, which makes our validation dataset clean and is not contaminated, has not been used, has not been seen by our hypothesis, okay, G. Okay. Now we can use the same relationship in terms of VC bound using the following relationship. So out of sample error of selected GM minus is upper bounded by e-validation performance of the same hypothesis, GM minus plus a complexity term, O of square root of logarithm m and k. M here is a total number of hypotheses we are considering. And k is the size of the validation dataset. Now the task is, in order to generalize well, minimize both e-validation and complexity term. Okay, so that is our new goal. We can think of using e-validation metric as our criteria to select or find a model among M models, okay, with a minimum e-validation error, right? Here, our algorithm learns a set of model hypotheses using dtrain, and we use e-validation on the final selected hypothesis to estimate or to evaluate its validation performance and select one of the model based on this error measure performance. Note that if you use e-validation for selecting our G minus hypothesis, denoted as G minus hypothesis, then the generalization guarantee can still be shown based on VC bound and analysis. And that e-validation is considered again a better proxy of out-of-sample error. Get the details of model selection via validation set or eval is shown graphically here. First, we take the entire data and split it into dtrain and devalidation. Okay. Second, we consider M hypothesis, H1 to HM, with different parameters, hyperparameters. Note that each H here can consist of thousands of different hypotheses, and each H hypothesis can be different, for example, perceptrons, different logistic regression, different linear regression hypothesis. And for each set hypothesis set, H1 to HM, the learning algorithm will select one final G1, okay, with the minus sign, G2, and GM using the dtrain, and usually based on the in-sample error performance. These are the finalists. Once we have G1 up to GM, we can use devalidation dataset to further assess their performance in terms of e-validation error and select one of these finalist hypotheses as a best model denoted by HM star, and then EM star represents the best e-validation error, while in this case the selecting HM star using the best e-validation error performance uses dtrain and devalidation. We can also consider using the entire training dataset without splitting and selecting GM star, let's say. So we are comparing two different approaches. Note that the given dataset has n points, right? And dval takes k points, and the remaining data points, n minus k, represents the amount of training dataset left for dtrain. The amount here is very important. It's crucial in selecting and comparing the generalization performance of, for example, HM star, okay, we call it as G, let's call it GM minus, okay, and comparing it against GM star. By changing size of dtrain and validation, we can generally show the following relationship holds. Out of sample error for GM star selected using entire training dataset is less than or equal to the out of sample error performance of the model selected using smaller training dataset n minus k and using e-validation. From the VC bound and then learning curve, we can say that if amount of training points is less, then the E out is poorly bounded, which may result in out of sample error performance of GM selected from the entire training data smaller or equal to the GM selected using the partial data. And E is further upper bounded by E validation of GM star plus its complexity term. Take a look at the role of K here. We established that the reliability of the estimate of the validation set is order of 1k, okay, square root of log m over k. The smaller the k size of the validation set, the worse is the estimate is, this estimate. Because here we want to minimize two terms, eval and then complexity term. And if we have small k, the second term will not be small. And on the other hand, if you have large, very large k, we would get a reliable estimate, okay, of a worst quantity of E out. Because E out decreases with the increase in the training set size. This is known from a VC bar, and size of which must decrease if we increase the validation set size. If we increase the validation set size, the size of dtrain will decrease, right? And the bound of E out would be loose. The size of K or validation set size plays an important role in selecting the best possible model. For instance, say you want to select between phi5 and phi10, the fifth order polynomial, 10th order polynomial. By varying the validation size, we can observe the behavior of fifth order, 10th order polynomial and the relationship between these two different hypotheses in terms of expected out of sample error and validation size as shown in this graph. So in blue we see the performance of fifth order polynomial, and in red let's say 10th order polynomial, for example. And we also have in sample based selection as this straight constant lane denoted by GM hat, which is not affected, as you can see, by the validation size because this hypothesis has been selected using in-sample error. And also, we will set a benchmark reference as these dashed lines as an optimal performance of the hypothesis that we are considering. We can say test performance. So we see that the validation curve for H5, 10 fifth order polynomial, goes down and then up as we increase the size of the validation, while this red line goes up. So increasing validation size again means decreasing training size because we are using the entire data we have, okay, to split into train and validation. And if you have less training size, the hypothesis will not generalize well. That can be seen with the upgoing curve, or here it's visible. Increasing validation means decreasing training. And decreasing training size, data size, means out of sample error of the select hypothesis is poor, goes up or loose. We can also take into account the complexity of the hypothesis. This curve, if you assume it's tensor polynomial, shows that it needs more data to perform well. Smaller out of sample error is associated with small k size. In turn, this means more training size, while H5, fifth order polynomial, requires, okay, not that big amount of trained data as this one would. Now we have the dilemma about the size of K validation size. Okay, G minus, for instance, if you use large K, then we would like to know the actual out of sample error performance of G. But we have only E validation of G minus, which is supposed to be an estimate of E out for G minus. Therefore, it is necessary for K to be small so that our G minus is fairly close to G for small k. Because the bigger k, the larger discrepancy, the difference between training set and then full set. And therefore, the larger difference between G minus selected and then G. Right? This creates again a dilemma because we want K to be large because expected out of sample error for GM star is small, right? To increase to increase the reliability of E validation as an estimate of out of sample error performance of the G minus. However, we have a practical rule of thumb for trade-off for identifying the optimal K size. Okay, so the practical rule of thumb is if you have endpoints, divide it into 5 and take one part as your validation set. So 1/5 part of your data. Okay, in other words, if you have 100 training examples, use 80 examples for training and 20 for validation. Let us consider an extreme case of a validation size by using a technique called leave one out. Here, given n examples, n training points, we first choose n minus 1 points for training and 1 point for validation. The dn val is denoted by a point that was left out. The final hypothesis learned from training dataset n minus 1 is called gn minus. this was trained on all examples except n, one of the examples. This is just single example left out. And then the validation error is then defined as simply the error on the left out point using the hypothesis derived from the set that excludes that point. Yeah, we can make sure that this estimate is an unbiased estimate. This can be repeated. This leave one out procedure can be repeated for every point in the dataset using dn. Okay, what's the common between every error measure is that it was computed using the hypothesis, using a training set of n-1 points, n-1 different points, okay? And then leave one out cross validation error, denoted by E, leave one out CV, cross validation error of H and A, can be defined as average of point-wide e-validation error, where the effective size of validation set is represented by cross-validation error, which is close to n, the entire data set. By considering the extreme case of validation set size, which was equal to 1, we hope that the leave one out cross validation obtained across all n points left out approximates the out of sample error better than the other types of the eval or evalidation error. Okay, based on the following reasoning. The smaller k leads us to better approximation of out of sample error, while large k for the given GE minus allows us to think that the validation is the better approximation of the E out for G minus. However, for small k, the leave one out error will be better approximating. Look at the illustration of the leave one out cross validation error. Here, given 3 points, we train 3 different models, linear models, and we can estimate leave one out cross validation error on this linear hypothesis as average across 3 left one out examples. So in the first case, we train on 2 points and estimate the leave one out error E1 as the difference here. And in the second iteration, we leave second point out and train our hypothesis on 2. Third case. And leave one out cross validation of this linear hypothesis will be the average of all 3. And this cross validation error can be interpreted as how well the linear model fits the data out of sample. If we consider this constant model on the same 3 points and estimate the leave one out cross validation, similar as this one, take the average of E1, E2, E3, we see that the constant model is clearly the better. Given 2 different models, choose the one with smallest leave one out cross validation error. Again, this error is a better approximation of the out of sample error because it captures all the possible variabilities of all error across individual single points. Let us revisit the case of handwritten digit recognition or classification problems, where we extracted 2 features from the raw digits. They are the symmetry and then average intensity. Here we have 500 points for training and use the rest for testing the hypothesis. And the task is to use cross-validation to determine a hypothesis that will give us a better out of sample error. We can consider selecting the hypothesis or the model using in-sample error, which can give us the perfect separation between blue and red points, regardless of their nonlinearity nature. While selecting the leave one out cross-validation based technique shows us the following hypothesis. Okay, and we see here the error and number of features used, the relationship. For example, in-sample error goes small as we increase the number of features used in our dataset. And this number of features actually corresponds to the number of features generated by a nonlinear transformation, a polynomial of 5th order, 10th order, 15th or 20th order that we can use. So also the task could be here interpreted as identify the best order of the polynomial so that we will obtain a better out of sample error. The red here corresponds to the idealized case of the out of sample error. The dark lines corresponds to the performance of our model when using different features, different polynomials transformation of our features. Okay? And what we can observe that cross-validation, okay, based model selection tracks the ideal out of sample error. If it goes up, it goes up. So the difference between two is not that huge. While in sample error deviates from out of sample error very much as we start using increased number of features which correspond to the higher degree of polynomials. So without the validation, if you use only in sample error, the performance of our model is 0, which is perfect. However, it can be shown that out of sample error for this case can be, for example, 2.5%, while the in sample, leave one out cross validation sample can be not 0 because there are some missing points. Okay, it can be higher than this in sample, but however, the out of sample error performance of this model selected will be better than this model. By looking at this graph again, where can we spot the point where the CV is small and is not deviating from out of sample? It's around 6, right? If you use 6 or the polynomial 6 features and apply our, let's say, this linear hypothesis, then we should expect to have a good model. So in practice, the models selected using leave one out cross validation error provides us better generalization of our model to unseen examples and is expected to track out of sample error. Therefore, it is one of the best methods for using to select model. One of the disadvantages of the leave one out cross-validation estimate is that the computation required for calculating this error, leave one out cross-validation error, requires an additional training per model, okay, which is not always possible when you have a big training data set. So if you have 100,000 data points, you may have to train your model 100,000 times minus 1. Well, except this doesn't apply to a special case like a linear regression hypothesis, which have analytic solution, one-step learning. It is nonetheless considered one of the stable way of estimating out of sample performance of our hypothesis, as it captures the variance of single point estimates. However, modern real-world problems involve huge amount of training data set. Therefore, the leave one out cross validation is not often used in practice. When we use leave one out, we have n training sessions on n minus 1 points each. However, what if we want to use more points training examples for validation? For example, we can take the data and break it into different faults, such as shown here in 10 faults, making it a 10-fault cross-validation. We use 1 fault for validation and the remaining 9 faults for training. In other words, it's similar to leave one out, except instead of leaving 1 point out, we leave out a chunk or fault. D4, for example, can contain 100 examples, 1,000 examples, okay? And this results in n K training sessions on n minus k points each. In practice, tenfold cross-validation is very useful, and it is cheaper to compute than to leave one out cross-validation, right? So similarly, the model is selected on the base of the minimum cross-validation error on the validation set. So here V is the number of faults or number of splits we can divide our data set. Most oftentimes, V is used to be equal to 10, or you can also use 5, okay? But this is just rule of thumb, right? Practical rule. So in practice, V-fault cross-validation is generally preferred over a single validation if computation allows, right? So a cross-fault validation. And usually 5-fault or 10-fault cross-validation generally works well. Okay, it's not necessarily to trade off V-fault with leave one out. So usually what we are dealing is either 10-fault or 5-fault cross-validation in selecting the model. And the nature of validation itself applies to, for example, we have all training models and you can select among different hypotheses. okay, in that model. And if you have all validation schemes using the validation tools, you can select among the hypothesis finalists. And if you have all testing methods available, then just you can use validation to evaluate. Okay, and we can say that the validation techniques are just still are optimistic than the true testing. It's an optimistic performance of the models. However, make sure that when you report your results, you should report test result, not the validation. Okay, the validation result just allows us to select one hypothesis, one model out of available all set of hypotheses, and final result should be report on test data set. Okay. Today we discussed different ways to select a model, and saw that selecting a model using in-sample error is not the best choice, and that the e-test based selection is not easy or feasible. We went on and saw the validation technique, which allowed us to select hypothesis using e-validation performance. We also saw the leave one out cross validation, which requires huge computation costs for acquiring an unbiased, almost unbiased estimate. Further, we also use v-fold cross-validation, where we divide the data into several folds and cross-validate our model. So remember that the regularization, okay, tried to estimate the overfit penalty, so that instead of minimizing just in-sample error, we minimize augmented error, which consists of in-sample error plus penalty or complexity term. While here validation techniques tries to estimate the actual out of sample error by minimizing e-validation. Those are the differences. Both regularization and validation techniques can be used to combat overfitting problem and also bad generalization problem. That's it for today. I'll see you around.